Okay, second video on trig identities. So, key idea. When working with trigonometric identities, we attempt to prove that both sides of the given equation are identical. To do so, we work separately on the two sides of the equation. Always, 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 you want to pick the more complicated side to start with. And you want to transform your chosen side into an equivalent expression. So basically, you want to make the left side and right side match up. So you can use your primary and reciprocal trig ratios. Remember, primary trig ratios are sine, cos, tan. Reciprocal trig ratios are cosecant, secant, and tangent. You can use this quotient identity that we've talked about. Remember, tan of theta equals sine theta over cosine theta. And you can use this new identity, which we haven't talked about, but which is going to be quite useful. Sine squared theta plus cos squared theta equals 1. So the way we're going to do this lesson is just by taking some examples and trying them out together. So why don't we just take this first one? I've got some space for us over here on this page. And we can just brute force method this. So we can just kind of make our way through, see how we do, and hopefully we'll be able to do a whole bunch together. Let's see how things go though. So this first example says 1 over sine squared x plus 1 over cosine squared x equals 1 over sine squared x cosine squared x. So again, when solving these identities, I want to make the left side of my equation equal to the right side of my equation. So I'm going to pick the more complicated side to start with, which in this case for me happens to be, the left side. So why don't I start by getting a common denominator? So I can take 1 over sine squared x and multiply it by cosine squared x over cosine squared x, just like that. I can do the same thing with 1 over cosine squared x. So I can multiply it by sine squared x over sine squared x. I'm going to end up with cosine squared x over cosine squared x times sine squared x plus sine squared x over cosine squared x sine squared x. Because I have a common denominator now, I can group up my two rationals under the common denominator. Now remember when we talked about this Pythagorean identity, sine squared x plus cosine squared x equals 1? Well, cosine squared x plus sine squared x, well, it doesn't really matter the way that I order these up. I can just replace them with 1. Now, cosine squared x sine squared x is the same thing as sine squared x cosine squared x. The only difference is they're just being multiplied in the reverse order. And remember, your order doesn't matter when you're multiplying. So all of this carries forward. I don't need to rewrite it million and one times. And therefore, left side equals right side as shown. Always, always, always put a little concluding statement like that, just to wrap up your work nice and neat. That is one thing I am a little bit picky about. So there we go. We've shown that both sides are equal and we've proven it. These are essentially proofs. We can take another one to do together. So maybe you guys want to do E, or we can do D. Why don't we do D together? Let's do D. So this says sine x plus cosine x squared equals 1 plus 2 sine x cos x. I'm going to start with my left side. This essentially is a perfect square, so why don't I rewrite it as sine x? I've made a mistake here. Sorry, let me just put that below. Sine x plus cosine x, bracket sine x plus cosine x. So we know our exponent just basically means multiply your term by itself. And now I can FOIL. So sine x times sine x is going to give us sine squared x. Sine x times cos x will give us sine x cos x. Cos x times sine x will give us cos x sine x. But again, your order doesn't matter with multiplication. It's the same thing as sine x cos x. And then cos x times cos x is cos squared x. So we have some like terms here that I can group up. That should give me 2 times sine x cos x plus cos squared x. And let me pair up sine squared x and cos squared x like this. And remember our Pythagorean identity? Sine squared x plus cos squared x is 1. So we have 1 plus 2 sine x cos x. And all this comes down. Therefore, left side equals right side as shown. And we've proven that this identity is true. I'll do one last one with you guys. So why don't we go ahead and pick I, maybe. I might be an okay one. As I'm just writing the question down, I'm just going to give you guys my 2 cents about this unit. Not this unit, I should say, but this lesson. Identities are kind of like solving puzzles, and they require you to be a bit creative in your approach. There is no procedure. I can't teach you how to do every single identity because the procedure you implement is different. The only thing to guide and inform your process is these hints here. So using our identity, using the quotient identity, which we haven't had to use yet, primary trig ratios. But what I've found is that the more practice you do, the better you get. And it really is one of those things where too much practice is not a bad thing. Like if you're just doing textbook questions, A to F, you probably don't need to do all of them for a regular unit, right? You just do some easy ones, you do some hard ones, and based on your understanding, you kind of figure out what you need to work on and what your strengths and weaknesses are. Well, with identities, you want to do as many as possible, and you want to do them all the time. So what I mean is every night go home, do 3 or 4 of them. The more you do, you really benefit from. The more you do, the more you start to see patterns that emerge. So that's my 2 cents. Do a bunch of them, do them frequently, the more the better, because they are quite tricky, and there is no one procedure fits all for these. Okay, let's start foiling here. So let's start with the left side. 1 times 1 will give us 1. 1 times negative cosine squared is negative cosine squared. Tan squared x times 1 is positive tan squared x. Tan squared x times negative cos squared x is negative tan squared x cos squared x. Okay, so far it's not looking very good. Let's see what we can do here. So I want to manipulate tan squared x and cos squared x. I've got an idea. Check this out. Remember what I was saying about patterns? Here you have to implement something from our factoring unit. So why don't I pull out a common factor by factoring these in pairs? And you'll see what's going to happen here. It's a beautiful thing. So pull out tan squared x from this and this. If you pull tan squared x from tan squared x, you should just be left with 1. And if you pull tan squared x from here, you should just be left with negative cos squared x. Check this out. Here you have 1 minus cos squared x. Here you have 1 minus cos squared x. I can common factor it out. And I should be left with 1 plus tan squared x. Because if I'm pulling 1 minus cos squared x from, like, just think about what happens if I take all of this and redistribute it again. I do get 1 minus cos squared x here, right? And over here, I do get tan squared x times 1 minus cos squared x. So just think what's going to happen if you redistribute. Does that help us? I don't know. It seems like it was just staring me in the face. Again, I don't have answers here. We're just kind of going through this together. But I think we're onto something here. So this gives us sine squared x. Is that going to help us? I'm not sure. Let's see what happens. Do I have to redistribute? I don't know. Nope. I got an idea. And we're going to have to be creative here. But you remember the Pythagorean identity? Sine squared x plus cos squared x equals 1. Let me manipulate it a little bit. And let me divide everything by cos squared x. So what I end up with is sine squared x over cos squared x, which is tan squared x. Cos squared x over cos squared x is 1. And over here, I have 1 over cos squared x. So I've taken my basic Pythagorean identity, manipulated it, and now I have an expression for tan squared x plus 1 over here. So all of this can just be replaced by 1 over cos squared x. So I had sine squared x times 1 over cosine squared x. And I'm running out of space here. So let me finish that up over here. Essentially what I'm going to end up with is sine squared x over cosine squared x. And that's the exact same thing as tan squared x. Because think about it. There's an intermediate step here where you could just replace this as sine x over cos x and bring the exponent outside. And then you can replace sine x with cos x. Or sorry, sine x cos x with tan x. Anyways, we get that the left side is equal to the right side, because that's what we started off with on the right side. And therefore, left side equals right side, as shown. So you see, I started off this problem. I had no idea what the answer was. We kind of, had to evoke a little bit of creativity to get to the final answer, but you'll get there eventually. So a whole bunch of problems here that you can try and make your way through. Again, you're going to get the most benefit from this if you actually give them a go. I recommend partnering up with a peer or maybe even two, because sometimes when you hit a roadblock, a different perspective or somebody else's opinion might go a long way in terms of getting you to see something you might not have seen otherwise. Give these a go. I'm wishing you all the best, and we'll chat about this to see if you guys have any questions. Good luck.